digitized and the power consumption of devices has significantly reduced in the recent years, which make it possible for people to instrument many different things with sensors and the devices. So this is a very important factor. And then on top of that, cloud computing is providing affordable computing power at scale. This allows users to connect to the devices and also store the data from devices. This is another contributing factor of the current exploding of Internet of Things. Then connectivity become ubiquitous. By that I mean there is a LoRa. How many of you heard about LoRa? It's a protocol. It's a, okay, thank you. We got a couple here in the room. It's a wide range Wi-Fi. And there is also narrowband IoT. You probably hear that. Narrowband IoT is a protocol for mobile data. Then, of course, there is a cellular data. It is those different protocols make the connection become affordable. Then on top of that, analytics technology also made significant improvement in the past few years. So it is ready today to handle the large volume of data that are generated from those IoT devices and sensors. That's why we see this trend up of adoption of IoT. There are a lot more IoT solutions, applications are built and applied today compared to 5 years ago. Now, IoT becomes such a broad topic. So all those together, they create opportunities to transform organizations to how they do things, how they operate, and even to what they do. By that, we mean because now with real-time data generated from those devices, we are able to really reduce the waste and improve operation efficiency, which lower the cost of running business. That's one significant benefit of Internet of Things. Also, with IoT, we are able to find new sources of revenues by providing new products and services that meet customers' requirements. That's the second benefit. IoT enable new products and business models. Because we are able to instrument products with the IoT sensors and devices, this allows us to really have the insight of a user of those products and how people interact with those products. Help us to improve the customer experience and the personalized service. If you think about the GPS, that's actually one example, right? Very easily, you have a smartphone when you drive here. Think about that's IoT devices that people are able, based on all the data feed in, we are able to find out the real time the traffic on certain road. That's enabled by your smartphone, which is a personal IoT devices. Okay, so the journey of building IoT solution normally have multiple phases. This is kind of each phase and step. First, we start with connect and gathering the data. Once we have the data from the devices and sensors, it allows us to really visualize the data and identify the pattern of those data. It is very important because the data itself is not interesting enough. Data just raw material. It only becomes interesting when we can identify certain pattern in those data. And once data are understood, it allows us to build models, analytics models, that can predict how the physical things behave in the world. Now it's become more interesting. It starts to connect to the line of business. Because the world today, the world never static. The world is keeping changing. So AI, artificial intelligence, really require continuous learning. You heard the word of machine learning. It is very important that we have to keep feeding the AI model with the real-time information so we can improve the accuracy of our prediction in the future and also reflect the changing world we live. So those are the different phases of IoT solutions. And IBM is one software vendor. We also have Amazon, Microsoft, PTC. Those are the major players in the IoT field. Each of those software vendors have a solution every single step along the journey. So we can take a quick look. Here are some examples of the industries that really adopt IoT. We start from automobile, connected vehicle. Vehicle today become the biggest mobile entity. And electronics, chemical and petroleum, healthcare and insurance are tied together. We're going to talk a little bit more there. Energy utility, retail. Retail actually use IoT devices to track the traffic. Transportation, logistic, manufacturing, aviation. Those are the major industries that adopt IoT. There's also this word you probably heard called industrial IoT. Those are the major industrial verticals. Okay, so I want to take IBM Watson IoT platform as an example. This is nothing unique. We start to see this common pattern emerged in the IoT field, that how we can build an IoT platform to address this market. Start from bottom of this chart. Normally, there are common services that we provide on cloud, on public cloud. Those provide essential function like the connectivity of a device, device management. On top of that, we also recognize some common patterns. So we pre-integrate among those devices, provide data lifecycle management, which is very important. Data lifecycle management is the foundation for any AI algorithm. Algorithm got to run against the data, so we need data lifecycle management there. So this is the common pattern we provide on top of the public services. And then we target different industry primary use cases along 3 different ways that we talk about. One is to improve the operation efficiency, lower the cost of running business. The second one will be identify new sources of revenues by providing new products and services through IoT solutions. The third one is leverage IoT to really improve customer experience, engagement, and personalized services. Those are the 3 ways that we leverage IoT to I would say, improve people's daily life and help business to advance. Any questions so far? Sure.
Elaborate a little bit about data management, lifecycle management.
Data lifecycle management. Yeah. Okay.
So, like specifically, what's the objective? What are the considerations? How does it play into the whole IoT ecosystem?
Yeah, great question. So there are tremendous data generated by IoT devices and sensors. First, you want to store the data, right? And the second, you want to do data cleansing and data, we call it manipulation, data enrichment. And thirdly, it's tremendous. We see our customer have 10 terabytes of data just in 1 month. And you want to provide a multi-level storage for the data. You don't want to have one all full year, calendar years of data in your real-time database. It will first be very costly. Second, it will slow down your data query and analytics performance. So this is what we call data life cycle management. And normally you store the latest data the past 7 days in a real-time high performance data storage. And then you put the past 3 months in some middle tier, and you put any data over 3 months in the low cost data storage. If you need to retrieve, you can, but most time you don't need to. This is what we call data life cycle management. And it is the foundation for analytics, very important. In most IoT solution, the most costly part is data storage. Yeah. Okay. Let me see which one. Okay, I'll use this one to dive a little bit deeper to talk about those essential IoT services. Start from connect. So most IoT patterns require bi-direction connection between the devices and the cloud. So one direction is for IoT data flow from devices to the cloud. Sometimes you have a gateway or edge there. The second direction will be command and control sent from cloud back to the device. For example, on my way vacation, right, on my way to the airport, I want to check whether my garage door is closed. I don't know if you guys, I normally don't remember, right? So with some application, we can easily send a query from my cell phone to the cloud, then back to the sensor on my garage door, say if garage door is closed or not, and the status return. If garage door is still open, I can send command close door on my way to the airport. That's very, I would say, simple use case here. And in this use case, you see bi-directional communication from a device to cloud. Second is called data capture, or somebody call it data ingestion. Once you have this data, you want to ingest the data into your data storage, data management. There are different ways of data ingestion. Could be real-time data, sensor data feeding, could be bulk data load, right? So that's there. Register really is, I prefer to call it data management. This is where security happened. This is where we used to authenticate, authorize, and do access control of the IoT devices. It is extremely important. You probably heard a few years ago there are people hack a baby monitor, right? You heard there's some guy's voice talking to your baby. This is a hacking into a devices. In this case, it's a baby monitor. Device management actually provide that guard, make sure it is authorized action. If it's not, it will card it down. So that's important guard. Analyze, we talked about, this is where the analytics algorithm run against data. Archive kind of tied to the data lifecycle management to reduce the total cost of ownership for IoT solutions. That's for cycle. On the right-hand side, I'm talking about, this is specific to IBM Watson IoT, that we price IoT solution based on device type. So from a sensor to customer, enterprise, industrial, it is going up. So for each device type, there are certain capability associated that for different services. As you go from a consumer to industrial, the capability going up, the price point also going up. To some extent, this is like your cell phone plan you pay. Pizza is here. And so we can pause for you guys to grab a bite and continue. You want to do that? Okay. We gave 5 minutes to go grab a bite. We'll continue. You guys want to grab something?
Sound
and
initially
it's very good. How can I turn off?
again, it should be good.
Okay. Okay, are we ready to resume? Everybody has a bite? Very good. I think we talk. Actually, there's a gentleman asked me a very interesting question towards the end. I'm going to share with you my thought. Okay. Oh, here. Sorry, we're connecting. Great. So this is the engagement journey of IoT solution. So first thing we do when building any solution or IoT solution is to sit down with a customer to understand what are the business objectives, what do we try to achieve with this piece of software or solution. Second, once we identify our business objective is to discovery. Discovery meaning what are the KPIs? KPI is a key performance indicator. Help us to achieve those goals, to identify those measurements, metrics. The next is based on this, we are going to design and build the software, write the code, right? That's the common words there. And then we deploy the solution. I should have mentioned that most IoT solutions and IoT platform services today are software as a service, meaning that the software vendor not just deliver the software to you, they also run this to you. For example, for IBM Watson IoT platform, my team also hosts the service for client. So client do not need to worry about the software upgrade operations. What's the hardware spec to run these services? We take care of that. So our customer can use IoT solution, IoT platform, just like a utility. You pay the monthly bill. The service will be there. There's this thing called service level agreement. Make sure the service will be up 99.95% of time, those kind of thing. So that's another trend you probably already know. Okay, we talk a lot about what are the key services of IoT platform. What are the industry IoT solutions target? I want to share with you one real example how IoT solution help business to lower their cost, improve the quality of services. CSOT is one of the world's leading LCD panel manufacturers. It's located in China. So LCD panel is an essential component in electronics devices. No matter it's large screen TV or your smartphone, it all have the LCD panel on it. This business is super competitive. The pressure is on for the manufacturers to really produce high quality products at low cost. No surprise. So for CSOT staying ahead of the competitors really mean they will continuously improve their production processes and also increase the quality standard. Now CSOT already done a great job. They already automate 95% of their manufacturing processes. However, there's one bottleneck remaining, which is called quality inspection. Inspection of the LCD panels that were produced. This inspection traditionally is done manually. Now, even with well-trained visual inspectors, there's still a risk that a defect slip away. When defects slip away, those LCD panels delivered to the device manufacturer, it's become very costly to return, and also this is a recall, right? Return and damage of the reputation. So now, besides that, it is significant effort to train visual inspector, and this job is very tedious, very boring. It is extremely important, very boring, time-consuming. So CSAUD worked with IBM to bring AI, we call visual inspection, quality insight, into their manufacturing floor. You can call it a smart manufacturing. So first, we sat down with the CSAUD customer and to identify, they actually build a library of tens of thousands of images captured from their production line. And they classify all those pictures into two categories. One is good products, the other is products with various production defects. So we create this library together. And then with our research team, we build image classification model. Use this library to train this image classification. Actually, let me go through here. So the AI model, in this case, is a visual inspection model. It's trained in cloud. Once the model is ready, we deploy from cloud to the edge server, which is located on manufacturing floor next to the inspection points. So in production, what we have is a high-definition camera on the manufacturing floor. We'll take a picture of the LCD panel. And then this picture is compared with the library. And the AI model runs on the edge server to classify this LCD panel, whether it's a good or defect panel. Each classification was assigned with a confidence level. And that confidence level is sent to the cloud. If the confidence level is below certain threshold, we will have a human inspector to review and evaluate. So by doing this, we will have a human expert only focus on the items that need attention, and that's less than 1%. This is how we can significantly reduce manual effort. And some questions? Go.
Same kind of result. Can you hear me?
Yeah, I can hear you. Mm-hmm.
Yeah, so I was just curious whether that type of technology is being applied to things like the FAA, air traffic controllers and stuff. It seems a very stressful job, very focused, and it seems like you could build in that type of technology and then have the AI alert the humans to focus their attention, taking some of the stress and also improving the success rate.
Yeah, so answer that question. I don't know personally whether FAA is using this type of AI technology. However, answer your question, yes, technically this can be used. Now, anything involved with safety or health have a higher regulation. So even we have a technology available today, there's lots of tests need to be done, lots of process we need to go through to really say we are going to use this technology, replace human effort, especially in health industry, anything related to safe. So answer question, yes, technology can be used. Then the process it's pretty long normally. Yeah, just make sure it's 100% safe for everyone.
Okay, so if you guys can have your questions kind of at the end of the, we have like a couple of speakers, so just trying to
Okay.
make the time.
I catch up. Yeah. Okay. So we talk about the LCD the confidence level was sent to the cloud for human inspection to take a look. We talk about there's a machine learning here. So there's a continuous learning. All those information, including the original library of an image, are fed into this AI model for continuous improvement of the accuracy of this visual inspection. So the continuous learning happens in the cloud, keep sending improvement to the model, runs on the edge. So this is a real example. By doing this, we reduce the average inspection time from 15 to 20 minutes to milliseconds. Okay. So actually, I'm pretty much almost done here. So I want to circle back, talk about, you may hear people talking about consumer IoT and people talking about industrial IoT. I would say the most popular use cases for consumer IoT is a smart home. And we talk about the industry. Industrial IoT really apply in manufacturing. It's called Industry 4.0, start from Germany. Logistic, healthcare and insurance always tied together. Agriculture, automobile. Now, the major differences between consumer IoT and the industrial IoT really lies in the IoT devices and the application. For example, people would think wearable like smart watch. Normally, it's used in consumer IoT. However, we also see the trend is emerging that consumer IoT and industrial IoT start to overlap because the technology behind this are not much different. It's the same. I'll give you a real example. It's my team did for worker safety. We use a wearable, which is a consumer IoT devices, to detect, for example, shipyard worker. Maybe they have a sudden fall, right? We will generate an alert. This is using consumer IoT wearable devices, apply that in industrial manufacturing. And also potentially could be insurance. So that's all I want to say is IoT is such a broad topic. So people talking about the consumer or industry, it's really focused on the specific IoT devices. The technology behind those, they are pretty much same. And we see the intersect of consumer and industrial IoT. So this is really the main part I have.
Well, maybe one or two questions just to wrap things up.
So I like your examples of the wearable technologies, between the industrial usage and consumers. Are there any really cool examples that we have not thought of that went from consumer use cases to industrial use case, or vice versa? Like those technologies switching around. Are there any examples that you can think of?
The closest example is really the wearables. My personal passion is really in the elderly care because I have my parents live in China. They're getting old, right? With wearables, can significantly improve the quality of life of elderly people because with that we can detach their intake, their movement, identify their the health condition, and this also apply in insurance. So this is an example from consumer devices to elderly care, which is an industry, to insurance, which is another industry. Yeah. Any other questions?
Okay.
Did you say that you were able to reduce the inspection time of the
Yes.
LCD displays to milliseconds.
Millisecond, yes.
Doesn't it require multiple patterns on the display?
It's more than multiple patterns. There's tens of thousands patterns identified. That's what the image classification algorithm will handle.
And you display all these patterns and take pictures of them and analyze them in milliseconds
No, millisecond means per panel.
per panel.
Per panel. Yeah.
Well, per pattern?
Per panel, LCD panel.
So how many patterns, visual patterns do you use?
Visual panel is a tens of thousands pattern. So it's really use a parallel, very powerful computer behind the scene to do this in parallel. That's why we are able to do this in millisecond. There's no comparison between this parallel computer and the human. There's no way.
So it just flashes all these different patterns? like,
Exactly.
extremely fast. The camera is following all of it, analyze it in almost real time.
Yeah, we use neurotechnology behind the scene. So it's much more complicated. There's a neurotechnology used to recognize any defects, to match.
I've heard a couple of examples now, or not examples, I've heard a couple of times that the industrial Internet of Things can help improve product development specifically.
Yeah.
I'm just curious how the feedback from IoT sensors in a factory floor can actually help the manufacturer improve the development of the product. What sort of things are they looking at, or is the sensor monitoring to help the manufacturer or distributor create a better version of their product?
I gave you example, not necessary manufacturing, but in the maintenance. We work with this Boeing, right? It's in trouble, but this is different. So used to be Boeing will do maintenance of their aircraft based on how many hours the aircraft is in service. Sounds reasonable, but a smarter way to do this is really based on the usage of certain pieces and parts. And how you can measure that is by the sensors attached to the parts. So I can find out the engine already flying for 200 hours, it needs maintenance, rather than the engine has been there for 2 weeks. Because if a full 2 weeks you park there, you don't necessarily need maintenance. But if 2 weeks you non-stop flying in the air, yeah, you probably don't need to take 2 weeks. 1 week you need maintenance. This is where we call it predictive maintenance, based on usage rather than calendar time. Yeah.
So are you measuring the actual component, or are you just recording the actual time it's being operated?
Individual component, individual parts, we instrument. Yeah.
So thank you, XP. That was an excellent, really engaging presentation. And if you guys have, I know you guys had a lot of questions. If you want to follow up, please post it on the meetup group, or maybe follow up with XP directly if he is willing. But,
Yeah, I'll be happy
thank you
to.
very much for
Thank
the
you.
Hook it up and hello. Okay, so we'll have the next presentation section from our sponsor. They have 2 guests and speakers. They'll introduce themselves, so we're waiting for that to set up. Please.
Okay. How about this one?
Yeah, this one is working. And
Yes. This is how we go. Okay, go. Yeah. So, yeah. Yeah, we'll do. Hi guys, thanks for coming in Thursday night. I know it's really hard to come over because it's like last week of March and everybody needs to go for some drink, and I'm so sorry that we didn't get beer this time. But if you can see, KX name next time in meetup, I will swear to God, I'll bring beers, like the cold beers every time. I know it's getting hot in Texas, and then I promise. I will have beer next time. So I just wanted to give us some head up. I'm not an engineer. I am, explorer from KX. So I'm based in Austin. So if you have any question after this meetup, this presentation, please come. Feel free to come to me. I'll just give you some notation about AnacondaCon. I'm pretty sure there will be some Python developers, machine learning, big data developers who are using Anaconda or who are familiar with Anaconda. We have strong partnership with them, and then we will be one of gold sponsors for AnacondaCon. We will have booth. We will also have some speaker session for a similar thing but different thing, from what we are doing today. So if there's anyone who's going to AnacondaCon, please feel free to come for our speaking, and we will have booth at number 6, for 3 whole days. So please feel free to stop by and talk to our machine learning engineers. Also, we have KX Ventures thing. So we are database engine provider, but at the same time we have this investment kind of project for startups who are data-driven startups, for machine learning or IoT or whatever related to geospatial. We have 17 in our portfolio right now. So if there's any startup companies who are looking for some scaling up or something, please come to me and talk to me. Also, if there's anyone who's looking for a job, please take a picture of this QR code. We are hiring for data scientists and developers everywhere in the world, from here and there. So yeah, that's almost everything that I want to talk about. And yeah, I will bring up Thurston, one of our speaker, and he will give you some introduction to IIoT, just like what XP did, with different and similar angles.
Do I need both of them?
We'll have all the presentation in our meetup as well, so you don't have to rush to take care. We have all the announcement and everything ready for you.
All right, good evening. I'll try and make this quick since the pizza's gone already. So I work with a company called BizTel. I'll explain who we are in just a little bit. We are an analytics company, though, based in the semiconductor business, moving out of that and into regular industrial applications. So a lot of what she was talking about before, the industrial Internet of Things, we deal with that on a daily basis. This is a 2017 survey kind of explaining what's driving a lot of that is, I think press and media tell everybody you need to have an industrial IoT set up in your factory. They say 80% of all manufacturers are investing in IoT. And it's based on trying to raise profitability and get better throughput in your factory, better quality. All those numbers are leveraged against these manufacturers, which pushes them into a situation where they want some sort of IoT investment and some sort of project to make those things happen. The focus for most manufacturing is actually predictive maintenance, as she mentioned before. There's a huge focus on being able to not go to time-based maintenance and push everything to predictive, where you know exactly when a piece of equipment needs some sort of maintenance. You do it at that time. It's saving you parts. It's saving you productivity. Everything is improved by doing that. The other kind of dream is self-optimizing production, where you have a factory that knows the best way to route some product. It knows these pieces of equipment are performing the best. I can route all of the materials through that and get the output that's desired. So those two are the biggest, I guess, push in manufacturing today. There is a lot of inventory management that's tied to those things as well. So being able to do predictive maintenance, a lot of it is focused on, you can predict when a piece of equipment's going to go down. You know the lead time of a certain part that's necessary for that maintenance to happen. So you predict the failure, you order the parts automatically, the parts show up the day before they need to be put into the equipment, and everything goes very smoothly and easily. So our applications that we develop are based on trying to make these dreams come true, I guess. A lot of that is being driven by sensors. So sensors are much, much cheaper and easier to come by now. So with MEMS devices, you've got small, low-power devices. In a lot of cases, you can have wireless battery-powered devices that you just stick like a sticker onto a piece of equipment. In factories, flow is a big deal. If you've got some sort of cooling water, chillers, dispense functionality, acoustic and vibration is big in I guess the kind of logistics departments, as well as anything that's being driven by a pump, a motor. So being able to predict that motor failing before it fails, in a lot of cases, like actually CSOT, we do projects with a supplier that supplies an overhead transport for those flat panel displays. And if they lose one of those transports that's moving those pieces of glass, they shut the line down, and they say it's $1 million an hour is what they're losing whenever that line is shut down, because they can't transport on that track anymore. And usually a flat panel sheet is actually multiple TVs worth, so it's not a small thing. And if they drop it, then it's a bigger mess, and it takes a long time to clean up. Acceleration, tilt, motion, torque. A lot of that's going into robot prediction, being able to detect when a robot's going down. In the semiconductor business, pretty much every piece of equipment now has multiple robots inside it that do all the wafer handling to move wafers from a load chamber to a production chamber. So that's a big piece, and those generally run around $100,000 a piece. So being able to predict that it's going to have some sort of a failure before it catastrophically fails is it's a lot of money it's saved, and usually a lot of downtime as well. As she mentioned, machine vision and optical as well. We do a lot of work actually in the steel industry. It's becoming more and more prevalent where they're inspecting steels, cold rolled steel as it comes out for defects, and being able to look at that steel and compare it to a good piece of steel, you're able to actually do a lot of detection that way. So the trouble with all these sensors is actually in the semiconductor business, pretty much everything runs about 60 hertz. So the usual data collection at a fab is running 1 data point per second. The challenge we face as a company is starting in semiconductor, our software and all of our platforms were built to deal with that frequency of data. Now moving into these new sensor types and the requirements from the customers, they go much, much higher. So pretty much everything is higher than what we actually are used to looking at. So a lot of the sound and vibration sensors have very high frequencies. EUV systems in a fab usually produce about 40,000 data points per second. Something like a wire bonder, which actually bonds the wires to a single chip, runs about 100,000 data points per second. So dealing with that has given us a lot more challenges, because traditionally we've run using relational databases to store all of our data. So that's been a lot of our issue, and a lot of how we ended up meeting KX was our customer requirements were exceeding the capability of our current systems. So industrial analytics capability, I'm not gonna read all these, but basically there's a large number of customers that we have that are actually still human powered. So if you drive a BMW, which I don't know if anybody in here does, I don't, but if you drive a BMW, your paint actually comes from guys carrying bags of pigment and dumping them into a giant vat along with chemicals. It takes them about 1 day of dumping all of the things into that vat and then mixing it for about a week. And then they spend 2 to 3 weeks adjusting the mix, because there's little to no controls and little to no sensor data that's involved in that. They use a clipboard and paper and write down exactly what they did, and then they have scientists that look at the outcoming paint and then adjust it. And so it takes them about 4 weeks to make a batch of 10,000 liters of paint. 1 week of that's the actual production, and they spend 2 to 3 weeks adjusting the paint to meet the specs for BMW. So that's where level 1 is, and level 2 is generally where the semiconductor business is, which is they're moving into productivity monitoring, trying to do root cause analytics, some equipment matching, where they try and make sure that in a factory with 100 similar pieces of equipment, those pieces match, and so they can run the same lot through any of those pieces of equipment and get the same results, as well as run-to-run process controls, which is kind of what I was talking about with the paint, where you feed back issues into the next batch so you don't have the same problems. So eventually you work those issues out. Level 3, which is the AI piece, there's some of the tier 1s are doing that now, just the most advanced ones. TSMC, Samsung, Hynix, they're working in those things, which is the starts of predictive maintenance, using deep learning to actually detect patterns within equipment and base your maintenance based on what you're seeing there. AI-based analysis, and then edge computing. So this is all a little new in the semiconductor world, and then we're finding moving into pharmaceutical and paint and steel. It's level 1 or level 2 at the best. So as BizTel, we were founded in 2000. We are headquartered in Seoul, Korea. We have an office here in Austin as well. We do have regional branches, kind of where the semiconductor business is. So we do analytics software. These are the customers that we service currently. So Samsung, SK Hynix, LG. The bottom is mostly the flat panel display, like she was mentioning before, with CSOT. So we do work with a lot of those in China as well. So doing all the analytics and fault detection software for these companies. One of our applications that is starting to leverage some of this IoT information that we have is equipment matching. So generally what we do is collect all the data from the equipment. At that point, we actually can compare all these different pieces of equipment, and we use this as a machine learning based analysis to detect all of the differences statistically between different pieces of equipment. And we do that for every single piece of data that's coming off the equipment, and then sort it and rank it based on a statistical analysis of its difference from the other pieces. This does help actually with being able to ramp pieces of equipment faster and being able to get more productivity out of the equipment that you do have by being able to figure out which piece of equipment is actually best to run lots through. HMP is our more generic industrial application. So it uses the same kind of trace-based analytics as well as machine learning to detect remaining useful life for equipment. So we collect data from the equipment, we do the health monitoring. Once we've started detecting failures, we classify all those different failures and build models to detect those failures so they don't happen again. And at that point, we can actually look at trends in the data and match the patterns in the signals to detect that remaining useful life so we can give a prediction. We're doing this currently. There's a lot of focus on vibration and logistics. So companies, mostly in Asia, but like UPS, where they have long sorting facilities. If they lose a motor in those things, the line can go down. So we do a lot of that kind of monitoring, overhead transport logistics, as well as a lot of pump companies in oil and gas and semiconductor. So there's been a lot of focus on that. We're moving into other types of sensors, so pressures, temperatures, voltage, current, all of those, and building these same models for different pieces of equipment. All of these are still challenged by the fact that up until we met KX, we were still running all these on relational databases. So the amount of time and the amount of difficulty in building algorithms that could access this data, do the analytics, and publish results was taking a lot of time. So we've actually used KX both on our Edge platform that we've developed, as well as our base analytics platforms. So it gives us the capability to do a lot more analytics a lot faster. So our trouble was in doing full trace analytics with all of that sensor data, all those data points. The actual analytics was taking us minutes in some cases. And so by using a time series database, we're actually able to take that data and put it in a proper database formatted for what the data is. And we're able to actually process it infinitely faster, honestly, than we were able to before. So it's given us a huge edge on being able to take care of that sensor data from IoT. So what we work with on the BizTel side at a factory is we've actually met a lot of partners. KX is one. We actually partner with a lot of sensor companies as well. And we've started building basically networks of sensors around the equipment because in a lot of cases, the equipment that we're dealing with, beyond the paint story that I told you, but even semiconductor equipment, which is kind of I guess, some of the more high-tech equipment, generally is running like a KX2 266 processor, which is probably older than some of the people in here, but with 8 megs of RAM, 16 megs of RAM. In some cases, they're being run by like mid-1980s, maybe 1990 PCs with little to no storage. So we're having to build a sensor net around those things that actually we put in our own sensors, and we actually put in gateways to connect to an edge device so we can actually bring out more data at a higher frequency and do analytics on the edge first, and then we move that up to a manager. And in some cases, we've also partnered with several cloud providers. So in semiconductor, not so much taking it to the cloud because they're very protective of their data, but on the other sides like steel manufacturing and some of the other, actually even flat panel, they do allow cloud for us. And then we communicate also with the customer systems to make sure that we're actually providing them the intelligence that we gather from their data. We help them make decisions in their MES system and ERP systems. So this is the summary. Basically, the IoT and smart manufacturing. I've been in semiconductor now for 20 plus years, so there's been a lot of talk about it for a long, long time. But the availability, I think, of sensors and software to do something with the data from those sensors have actually kind of brought it to where it is something that can be a reality if the customer pushes hard enough in that direction. Equipment itself is not smart in most cases. So I think the majority of the capital equipment, as I mentioned, it was designed in the 1990s, and it's not broke, so nobody's fixing it. So having the capability to add to that equipment and build sensors into the equipment and use a gateway to actually bring that data out is something that has to happen. And I think there's a lot of companies that are doing that sort of thing now. I mean, you can look at just about any kind of IoT gateway device, and they have a litany of sensors that they support. And so you plug that gateway into sensors, and then you've got data coming off a piece of equipment that normally would give you nothing. So the other thing is that I've learned is as customers need to use the best of breed, a lot of our customers that we do get, it's their second time around. They tried doing something themselves, or they tried doing something with the cheapest option they could find. Generally, it doesn't end well for them, and it usually takes 2 to 3 years and puts them behind the competition in a lot of cases. So I think looking for the best solution is in the best interest of all the customers that are out there. And then finally, focusing on the target. The other trouble that I have as a business development guy is I go and I talk to customers, and they want, and no offense to IBM or Watson, but they want Watson making all the decisions for a factory from day one, and they don't understand that their equipment doesn't even send any data out. So there's steps that need to be made, and you can have an end goal in mind, but there's a lot of steps that you have to take. You can't do predictive maintenance if you don't have data. You can't you have to collect the foundation and then build on that, which is something that it takes patience, and it takes a plan, but I think by getting people to focus on that more is something that ultimately it can make you successful at every step. If you shoot for the moon and miss, then a lot of times it's a big problem. So that is something I've learned. So that is everything for me. If you have any questions. Oh, no question. Okay. A lot of that actually depends on the customer. So there's a lot more focus now on traceability for components, especially like even at the cell phone level because of issues that people have had. So generally in our system, we'll keep about 3 months worth of data, but then the customer themselves will actually have an archive where they actually hold on to it much, much longer, because like generally the data will go from a fab to a back-end facility, to a packaging facility, then to the end user. So they keep the data until the end user's device is assembled and put out in the field, so they can have some reliability and traceability after the fact. Sensor failure, we actually have built some algorithms to look at data quality. So in prediction, when we're looking to predict, say, the failure of a motor, we actually are continuously calculating the sensor data quality at the same time. So we have thresholds that we set on that to where we expect a certain level of data coming out of the sensor. So that's what we look at there. As far as physically dealing with it, usually our sensors all come from partners that we have, so they will actually do the replacement of them. But if we see data quality issues, we can address those by detecting the same way we would detect a failure. All right, thank you very much. Thank you.
Hi everyone. Yeah, you guys can, you can hear me, yeah. Yeah, it's all good. I know we're a little pressed for time, so I'll get through this quickly, and like KDB, will be nice and fast. This is the one. Cool. So, my name is Thomas Walsh. I'm a KDB consultant for KX. I'm not sure how many of you heard of KX or KDB before this meetup, but hopefully you'll have a really good idea by the end of this. I'll be presenting the topic of KX from Wall Street to the Internet of Things. So this is about applying the technology that we've learned from the financial sector and applying it to other sectors that have been meeting similar issues with the growth of the interconnectivity of devices and the massive increase in the output of data. So there's a good case study already on our front screen with our partnership with the Red Bull racing team. They started to use us to help them with their real-time analytics during their races, and it's a very exciting partnership that we're very proud of to get started on. So I'll talk about IoT a bit. I don't think I need too much because I think it's been very well described already. I'll give you a background on KX and KDB and what the technology is capable of. I'll run through a quick use case of it outside of the financial sector. And then if we have time, I might be able to run a quick machine learning demo using KDB and Python. So, like I said, Internet of Things, don't think we need to talk about. The main takeaway is that we're seeing a huge growth in data, and that with the history of KX and KDB technology, we're primed to deal with these issues because the financial sector had a similar revolution 20 years ago with massive growth in technology and in the data output, and that we were able to help them solve those issues. So KX, we were founded in '93 by Arthur Whitney. The parent company is called First Derivatives, which was founded in '96 by Brian Conlon. We're headquartered in Northern Ireland, and we're listed on the London Stock Exchange. We've grown a lot in the last couple of years. We've grown up to 2,600 employees, and we have offices all over the world, from New York, London, Sydney, Hong Kong, and so on. This is just going to give you a quick breakdown of our different clients and partners to show the diversity of sectors that we work in. There's a very strong background there in the financial sector. I don't know, it changed. Which is that's where we got our experience in the big data analytics field. So it's big names like Citadel, Goldman Sachs, Morgan Stanley. There's a lot of them. But recently we started diversifying into different sectors. Like I mentioned already, the F1 racing teams. We also have experience working with aeronautics and space technology. And we're also involved with utility companies and manufacturing as well. So KX technology at its core is about KDB and Q. KDB is the world's fastest time series database, and it enables you to do real-time and historical data analysis by using a very small hardware footprint. KDB itself is just a database. It stores information in columns, and you can relate to other tables very easily, which is crucial for time series databases. It allows for streaming real-time and historical data, like I said, but unlike most databasing languages, you're able to query and run analytics at the same time, so that increases performance overall and reduces time to run your analytics. We now, like before, we used to be only locally on servers or on your machines, but we also have started to move into the cloud, most notably recently with our AWS partnership. Our solutions are vertically and horizontally scalable, and another big plus is that we're now able to interface with a lot of different technologies and languages at the same time to marry the strengths of KDB and Q with the strengths of other languages as well. I'll just quickly describe what time series data, because it's quite important. It's essentially rows of information that have been timestamped either by when the event occurred or when it's been recorded. So obviously in the financial sector, that's about recording when a trade occurred and having the price and volume information attached to it. But now we're seeing time series data grow into other fields, for example, in the sensors and in logging in general. And so with our experience from finance, we can definitely tackle issues involving time series data. Just to quickly point out that KDB is very powerful. These are just a few statistics about it. We're able to ingest data at very high volumes very quickly. We're able to analyze analytics in large amounts very quickly as well. And we have very efficient storage, whereby we can store a lot of information and compress it very well, and also retrieve it very quickly by the method that we store it. And I suppose the main proof of how powerful KDB is that it's been trusted by almost all the top investment banks around the world, and in some cases they've been using it for the past 20 years. So if they didn't rely on it, or if they didn't trust it, they wouldn't use it. They would just get rid of it. And if anything, we've seen a growth in the application of KDB, not only in financial sector, but also in other sectors, like I said. And what's crucial for time series databases and our applications is that we have very low latency. So between the time an event occurred and the time we recorded, it's a very small delay that you can almost react straight away to what is happening. And again, just to hammer home the point, our performance against other databasing technologies, these were some of our benchmarks against similar databases, running over the same queries with the same data. We were able to run far more queries per second than anything comparable. So once again, very powerful, reliable technology. This is just a quick case study about the application of KDB outside of the financial sector. So what we did here was we worked with the Independent Electricity System Operator. This is a utility company in Ontario, Canada. And so they used KX and KDB technology to suppose, supercharge their current system because their traditional database technology just couldn't handle the increase in data volumes and the increase in queries being run by their customers. So we saw volumes of about 135 million sensors per day, and we also had to maintain their historical database, which went back about 9 years and held over 350 billion sensor reads. And here's just the results of our case study. So this is before and after our implementation. Before, it took a long time to query and run basic queries, like about 30 seconds, whereas now the customers are able to get almost instantaneous results, so they don't even notice that the query took a bit of time. We've also increased the amount of power that the database is able to do. So before, they could only handle about 30 queries per second, but now it's 500 plus. So they're able to host far more demand than before. And we've also increased the amount of service that they have available to their customers. This next part is about describing our interfacing with other technologies. So we have this Fusion initiative whereby you can use the power of KDB with the power of other languages to try to get an optimized solution and use the best of both worlds. So with the KX license, integrations are freely supported, and there's plenty of documentation of how to implement them. We are able to connect to a lot of different languages. This is only a select few. I'll go through Python in a bit more detail. We also have an AI application with H2O AI. But this is a field that we're very excited in, and it matters a lot in IoT because we're able to run far more complex analytics by using KDB with one of these languages. So a use case that I'll describe is machine learning using KX. So what this slide is going to show you is how to use the best of both worlds. So the first 80% is using KDB mainly. So the strength of KDB is about querying, preparing, and analyzing data. And then what we're going to do is we're going to use the last 20% there to run Python and its rich machine learning algorithms and libraries to run over the data set that we've prepared for it. And so together we create a much more optimized solution, because before it might take, if you just use Python by itself, it would take ages just to do the first 80%, because it's not really designed to query and run large data sets. It's more about using complex algorithms. And so KDB will do that for Python, and we'll get our results much quicker than we would have before. Yeah. Do we have time for? This is actually quite applicable to what was being talked about earlier. So this is a case study of detecting abnormalities in semiconductor production. So what's important to learn here is that this was just a basic machine learning application. But what I'll show you is by using KDB alongside Python to run this analysis. So in this case, what we were trying to do is trying to optimize the way of identifying irregularities or abnormalities in semiconductor plates or their wafers, so that we can eliminate them from the manufacturing far earlier than they would have been before. So I'll just walk through this quickly. So all we're doing here is we're opening up a queue session, and what we'll do is we'll bring in all these libraries and prepare the data in queue, run the analytics, and fix the data ready for Python, and then Python will just quickly do this machine learning models and come up with its solutions. So the first thing I do is just load in our libraries, which is what it's doing here. I then bring in the data, and then you can see here this is our timestamp data, which is basically readings for a sensor wafer combination, and it also reads these 6 different features. So these features will be characteristics of the semiconductor wafer itself. So it'll be things like its conductivity or the pressure that was produced at, or its temperature, for example. And then next, we're going to use Q again to, before I go on, this is also our target data set, which is describing what the abnormalities are compared to the normalities, I suppose, in the data set. So it's not a very good set of wafers, because about 10% of them are abnormal, and 90% of them are fine and meet the standards required. So the first set is to bring in our different feature functions. And so we run these functions on top of the data set. And what that will do is that will create a larger table of different statistical analysis about each wafer sensor combination. And then the next stage is to then clean out all the noise. So what we'll do here is, again, using Q and KDB, is to find which features and which statistics that we've calculated are actually irrelevant. So if there's no relations between them at all. So what happens is we actually reduce the data set from 217 columns to 146 columns very quickly. So now the data is ready for Python to run its machine learning models on top of it just to do its job. And the first thing we do here is we just format the data that it's Python friendly, and then we also create a benchmark just to test out if our statistical analysis is actually useful or not. And so this next part is now importing the Python libraries into Q and setting up all our machine learning algorithms. We run this, and then the next part is about separating out our data. So for when you're doing machine learning modeling, which I'm sure maybe some of you have done before, you need to separate out your data set between your training data set and your test data set. And so what this is doing is it's splitting up randomly to make it as fair as possible. We then run the models to try and find an optimized solution for how to detect the abnormalities in the semiconductors based off of the readings. And we do that twice. So we do it once for our very accurately, with our very big data set of all these different features. And then we do it again with our just basic benchmark one, which just took averages of all the different features. And then we run them together. And so in this case, what we see is in the in our first data set of statistical data, we were able to accurately predict which wafer was abnormal or normal 99% of the time. So it incorrectly labeled 2 wafers out of a set of about 1,200. Without using that statistical analysis, it only identified, mislabeled, 7 of them, which means it's about 97% accurate. This may not seem big, but when it comes to manufacturing process, we're talking about orders of magnitude much bigger than just 1,000. So in reality, it's actually a huge saving that we would see. And this is just a quick matrix to show how it predicted it correctly or not. So it was correctly predicted all the abnormal ones from the test data set and only mislabeled 2 normal ones incorrectly. So the main point of this was just to show that you can use KDB and Python together to optimize your machine learning models and uses in your work. Just go back. So just to finish up for you guys, I suppose the important thing to note is that KDB is just the fastest time series database available, and it's very powerful because you're able to run real-time and historical information at the same time. You're able to query and also analyze data instantaneously. We've seen a lot of trust put into us from financial firms, and now we're starting to move into different sectors in the Internet of Things. So things like I said, utilities, the automotive industry, telecommunications, and so on. That's all from me. I'm I'm happy to answer any questions. Yeah.
Notebook you shared, is it gonna be available to the?
Yeah, I can share that online. I should have noted actually, the notebook that I used was actually using via Anaconda. So I used Anaconda to open up the Jupyter Q notebooks. These are available on code.kx, but I can share them with you if you want.
And follow-up is like, you mentioned you're using Python, but are you using any of the scikit-learn library? I couldn't make out your scope. It looks like you're doing some kind of your own coding.
I'm not 100% sure. It'll be up in our documentation which library we used. Oh, we were using the Fresh library, if that makes sense. So it was the feature analysis one.
Yeah, we can talk it offline, but
Yeah.
it looks like you're loading the objects into your queue space and doing something, or maybe I'm reading it.
So yeah, so everything's from the perspective of Q. So we import the library into Q and then run it as if it was Q. Yeah.
So that's why the syntax works.
That's why the syntax is different. Yeah. So yeah, that's exactly right.
Pythonish. Okay.
Yeah. Yeah.
Just additionally, you can do the vice versa. So you can use KDB Plus in Python. Just by loading KDB Plus to the library, because you can do that. You can download KDB library in Anaconda directly, and then just read it in the Python library.
Okay. Yeah, I think that might be more useful. Or
Yeah. So sorry. Yeah. So I was using.
example for our group.
Yeah. So.
Something you could share maybe offline later.
Yeah. So I was using Embed Py, which is for a KDB developer to use a Python. We have PyQ where you can do the opposite, where you can be a Python developer and bring in KDB. Any other questions? Yeah. Yes. So what I was doing is I was running numerous functions and doing all the aggregations in KDB, so that Python would have all the data points it already needs. Okay. All right. All right. Thank you very much.
That was a very excellent presentation. Thank you, KX, for sponsoring us, and hope to be working with you in future. And I apologize for the delay and the pizza being late, but at least we got it. So anyway, thanks for coming. With that, we'll close today's meetup. Thank you.